we're going to talk about sensors in this section. We're going to talk about the principles of sensors and how data acquisition is done, how the analog digital conversion is done, and we're going to, if we have time, we're going to move on to talk about how we use PIC Microcontroller to perform sensing. And finally, we're going to talk about the first lab, sensor design and data acquisition. Here's the outline. We're going to start with some general introduction of sensors, and then we're going to talk about how we interface sensors to an embedded system. We will explain the principles behind sensor data conversion and acquisition. We'll show you some examples. And after that, we will look at how we can use and program a PIC microcontroller to perform sensor data acquisition. And finally, we're going to spend a few minutes on talking about the details of Lab 1. Let's start with some principles. We're going to look at several concepts here. Transducer is a general term that refers to a device which converts energy from one form to another. It consists of a broad range of devices. The energy form could be electrical or magnetics or temperature or pressure. Transducer is to convert the energy from one form to another. The next two are examples of transducers. Sensor, that is a device which can convert a physical parameter to an electric output. A physical parameter could be, for example, pressure, temperature, light intensity, etc. And we want a device that can convert these physical properties to an electric output. It is because it's easier for us to process electric output as a signal. We have a number of tools or methods to further process this electric signal. Okay, that's why we want this sensor. We want this sensor to convert the energy from certain physical property to electric output. On the other hand, actuator is doing the opposite. It's going to convert an electric signal to a physical output. Okay. One good example is a speaker. Okay. A speaker is a device that converts electric signal to sound waves. Okay. That's one way to do the conversion. One example. The other example is electric motor. So you convert the electric energy into motion. Right? That's another example of actuator. You can easily have a long list of sensors. You can have cameras, which has image sensors. You can have an accelerometer in your phone, a gyro, often in your phone nowadays, a string gauge, which can measure the stress of a string. And you can have microphones that can pick up sound waves and convert that into electric signals. And many other ones, magnetometer, chemical sensors, optical sensors, etc. We have two kinds of sensors in terms of the format of the signal. One is analog, one is digital. For analog sensors, it output continuously varying output. Many sensors belong to this category. You can also find some digital sensors will give you on-off status or pulse trains. Photoresistor is a typical example of sensor. photoresistor is also called light-dependent resistor, or LDR. It has a very special property. Its resistance decreases with increasing light intensity. It's made of semiconductors, and the way it works is because photons are absorbed and by the resistor, it will cause electrons to jump into conduction band. When it moves through the conduction band, we have more electrons than the you have smaller resistance, right? So using this kind of device, you can detect the light intensity. The changes in the light intensity will cause the change in the resistance of that photoresistor. And the picture shows the actual component, and the bottom right is the symbol that we often use. For those of you who haven't looked at Lab 1, we are going to use photoresistor in our Lab 1 as a sensor to measure the surrounding light intensity. After you have a sensor, you want to think about how are we going to connect this sensor to my microcontroller or microprocessor based system, because my system is good at processing electric signals and digital signals. So we're going to look at next how we're going to interface this sensor with my system. Here's a very simple design. Okay? What you see here is a voltage divider circuit. Okay? We have two resistors. One is fixed value R2. The other one is R1. That's the photoresistor we can use. And we connect these two resistors in a series. So we form this circuit, and we measure the voltage at the photoresistor. Using Ohm's law, you can easily get to this formula. Using the supply voltage and the resistance of these two resistors, you can calculate the voltage. Right? When light intensity changes, the resistance of this R1 will change. As a result, the output voltage V will change. Okay? And that's the electric output coming out of the sensor. So the next step is we're going to take this voltage, use it as an input to our system, and specifically we're going to use it as the input to our analog to digital converter unit, or ADC, so that we can convert this analog signal into a digital value. Because our microcontrollers and microprocessors are good at processing digital signals. We do need this digital value. So moving forward, we need to understand analog digital converter, or ADC. There are different ways to implement this function, analog to digital conversion. Here are some types of ADCs. Integrating ADC. Integrating ADC, internally it has an oscillator and an integrator. You will apply the input voltage to the integrator. Also, you can apply a reference voltage to the integrator. As time goes, these input voltage will gradually ramping up, and the reference voltage will be the threshold where you can know by how much time this input voltage causes the output of the integrator to be a 0. Using this reference voltage and the oscillator for the time, you can then estimate the input voltage level. and convert that to a digital value. The second type is so-called successive approximation ADC. Here you basically have a changing analog reference voltage. You keep comparing the voltage with this input voltage. If the input voltage is smaller than the reference voltage, you put in a 0 to a shift register, then reduce the reference voltage, and then you compare it again. If the input voltage is greater than this reference voltage, you put a 1 in a shift register, and so on. So after several iterations, you can get the digital value of this input voltage. The third type is so-called flash ADC, which has the highest performance because it has a set of parallel comparators. The input voltage will be compared to reference voltage in parallel. So instantly, you can get the digital value from all these parallel comparators. So that's why this type of ADC is very good at speed. When you choose an ADC, you do care about certain metrics. The most important one is the sampling rate, or sample rate. It's defined as samples per second. So you can do 100 samples per second, or even 1,000 samples per second, depending on the requirement. And of course, the faster, the better, and the more expensive. Nyquist frequency, the idea is that you have to have at least double the sampling frequency than the actual signal frequency in order to have a meaningful result. If your signal, you know, it's vibrating, fluctuating at 10 kHz, for the sampling rate, you want to have at least 20 kHz, okay, in order to get a meaningful value from the signal. The other metric you care about the ADC chip is the resolution. Resolution refers to the data width or data size of the digital value of the ADC outputs. It is the accuracy of each sample. For example, you can have a 8-bit ADC or 11-bit ADC, etc. Higher resolution is not always required or useful. To understand this, let's look at this example. Let's say you have a temperature sensor that goes from 0 degrees C to 100 degrees C with an accuracy of plus minus 0.5 degrees C. Okay? That means the temperature sensor really have these 200 steps, okay, in terms of the accuracy. Right? If you do divide 100 by the 0.5, you got 200 steps. That implies you only need 200 different values to represent the degrees, the temperature. So as long as you have 8-bit from the ADC, you are fine, because 8-bit can give you 256 different values, which are more than enough to represent these 200 different values. When we go with higher resolution, 11-bit, you get finer granularity, but the temperature sensor itself only has 200 steps, so the higher resolution is not useful. To calculate the original analog value using the digital value, we can use a formula like this. The signal, the analog value, is the sample, or the actual digital value output from the ADC, divided by the max value, or the whole range of the value, and then multiply the reference voltage. So for example, if we have sample value is 153 and the max value is 255 and the reference voltage is 5 volts, Using this formula, we can know that the voltage from the sensor output is roughly 3 volts. Now let's look at a real chip, an ADC chip. This is a chip from Analog Devices. It's called AD670. It's a very popular ADC chip. I want to point out that we are not going to use this chip in our labs because the PIC we use has on-chip ADC unit. But I want to use this chip as an example to show you what are the things we need to consider if we want to use such a chip as a part of our system. This chip is a 20-pin DIP package. DIP is dual inline package. The resolution is 8-bit. It has a microprocessor bus interface. This is interesting because that means you can connect this chip directly onto the data bus of the system to the microprocessor. The conversion speed is 10 microseconds. It has 2 input ranges that we're going to look at. And the good thing is no external components required. Especially, it doesn't require a crystal or oscillator to generate clock. Some other ADC chips, older ones, may require a oscillator to generate clock signal. Internally, it has instrumentation amplifier, DAC comparators, successive approximation register, buffers, etc. The main control pins of this chip is the following. First is the read-write control, R/W with a star or sometimes with a bar. That means this is a signal with 2 values. 0 means write because the star by the W with the bar on top of the W. That means that's 0 active. So 0 means write. In this case, write means start conversion. 1 means read. CS and CE, you often see these control signals for these ICs. CS stands for chip select, CE stands for chip enable. In this case, both of them are active low, which means that if you want this chip to work, you have to give zeros on both of these pins, or logic low on both of these pins. The next one is the status. It's another pin, it's a 1-bit. It indicates this current status of this ADC, with 1 indicating a conversion is in process. So you have to wait until this status becomes 0, which indicates the completion of the conversion. We have 8-bit data bus and high impedance unless RW is 1, CS and CE is 0. High impedance is a very important feature or requirement on these ICs. High impedance refers to the fact that this chip can be seen as isolated from the bus if it's not in the operation mode, or it's not outputting data. This feature is important. Why? Why we want to have a chance or to be able to isolate this chip from the data bus? Yes. For a data bus, it's a bus, so many devices will be connecting to this bus. Okay? So you can have this ADC, you can have memory component, you can have all other different kinds of things connect to this data bus. But since it's a bus, you do not want 2 components outputting at the same time. What if one is outputting 0, the other one is outputting 1? Right? It's going to cause the corruption of the signals. So this high impedance will make sure that if this chip is not instructed to talk, it should not talk. It should not outputting any signals. In other words, it should keep itself in high impedance mode so that other components can outputting signal. Read cycle ends when either CS or CE brought to high. For the conversion process, any conversion will start until the current, well, any conversion start commands will be ignored until the current conversion ends. So you cannot interrupt the conversion process. Now we want to look at the input and output of this chip. For input, you know that you're going to input a voltage. Okay? Now for input out voltage, you have two scenarios, two common scenarios. And both are supported by this chip. First scenario is called bipolar. You have the ground signal, but you can have a voltage that swing across different polarity. You can go beyond, above this 0 volt, you can go below, or negative volts. So bipolar refers to the fact that this input signal can go positive or negative. Unipolar, on the other hand, is just one polarity, just positive. Okay? You can use one control pin, this BPO/UPO, to tell the chip whether you should accept bipolar signal or unipolar signal. Okay? BIO/UPO, 1 means bipolar, 0 means UPO. Note the star or the bar. That's indication of active low. For the input ranges, it has 4 ranges. The first two are the unipolar case. You can go from 0 volt to 2.5 volts, or you can do from 0 millivolt to 255 millivolts. Basically, that's a 10 times difference. And you do have control signal to, in fact, you do have different connections for setting these input spans. For output format, we know that we're going to have a digital value as the output, but we do have the option how we're going to represent this digital value. We have 2 options for this case. We can either do 2's complement. Okay? You can use the most significant bit to represent the sign bit, okay, to represent the positive value or negative value. Or you can use the offset binary, which does not have a signal bit, sign bit. For input voltage range, it's determined by how you connect these input pins. The top one is how you connect these input pins for doing the ADC on range 0 volt to 2.55 volts. I won't go into the detail here, but you can see by connecting the pins differently, you can select different input voltage ranges. For output, as we said that we can represent either a unipolar value or bipolar value, so it could be a positive or negative, or only positive. The first case, on the table on the top, is the unipolar case, where we do not have negative values. We have the straight binary representation. The table below is the bipolar output codes to represent the differences of the voltage, some are positive value, some are negative value. We can either use offset binary or use the 2's complement. In 2's complement, we use the most significant bit to represent negative values. Okay, this is the internal architecture of the chip. Although I don't expect you to understand this internal architecture, but I do want to point out this truth table for the control signal. By the way, these pictures, these tables are coming from the datasheet. When you work with any IC chips, you need to get access to the datasheet. Same for the PIC microcontroller you're going to program. You need to get the datasheet. Right? That is the Bible for the chip. It tells you everything about the chip, how to program it, how to connect it, if anything wrong, how do you troubleshoot. This table is the control signal truth table, where you can see that in order for this chip to work, you have to have both CS and CE signals are zeros. And then, depending on what you have on R or W, that pin, you can control the operation, either start the conversion or read the data. Another piece of information, very important information you can get from the datasheet is the timing diagram. Each chip has its own specific timing diagram for different operations. On the top left here, this is the write conversion start timing. What you see is a list of the control signals: R/W, CS, CE, format, status. Well, status is not really a control signal, it's a status signal. And as a part of this diagram, you see these waves, right, representing different options, different values that are possible on these control signals. For example, what we are trying to do here is we're gonna apply 0 to our W, which means we want to do start a conversion, and we apply 0 on CS to select this chip, and we at some point we apply 0 to CE, and once we have this, we know the conversion is going to start. Now, one example you probably cannot see very clearly, but what's shown here between this dashed line and the rising edge of this status, this small gap here, this is what's called TDC. DC is the subscript of this symbol. This is the delay to conversion. Okay? It's the time that it takes for this chip to respond to the control signals before it actually starts doing the conversion. Yes?
Do we have to like use something to try to like fix that or like in the lab?
No, we will not use this particular chip in the lab. But in your real work, if you ever use this chip, you need to be careful on the timing. Okay? Not necessarily on this TDC, but most importantly, you want to know the, for example, the delay from, for example, this here, delay from status low to data read. You have to make sure that you have enough delay before you read the data, because if you read too quickly, the data will not show up on the data bus. So for certain cases, if your controller chip running at a faster frequency, higher speed, if you do not consider this delay, you end up having the processor reading a value that is not the true output from the ADC. That's some garbage value on the bus because you're reading too quickly. Okay? So there are cases, these timings are very important. When you see something wrong, think about it. Look at these data sheets, look at the delay, look at the timing. Try to play around with the timing of these two parts or several different parts to see if there are any possibility of any inconsistent design. Okay, next we're gonna look at example how we're gonna connect this ADC chip to a microcomputer system, embedded computer system. We said earlier that this chip has a microprocessor interface. Specifically, it has this data bus. Okay, it has 8-bit data bus from DB0 to DB7. And it has these other control signals: BP0, UPO, format, CE, CS, and read write. Now, this figure shows a possible option, design option, how you connect a microcontroller or microprocessor with this ADC chip. In this example, the way it's connected, we connect the data bus, okay, of this processor system to this data bus of the ADC. Now, in this case, this 8-bit data bus is actually multiplexed. As you can see, you see this D0 through D7, but also A2 through A9. Okay. The way you, well, the other pins, for example, I'll write coming from the microprocessor system and putting into a OR gate and to this chip enable. That means either read or write operation will make this as a 0. I think we're missing the bar here. Okay. And the higher address pins are connected to an address decoder, and the output of the decoder is connected to chip select. So as long as you have a specific address, this decoder will output a 0 that will select this chip. Okay. And finally, we use the highest address pin to as the read and write control. So depending on the address you use, you're going to either start a conversion or read data. Okay? So this is just one option. Okay? It's not the definite answer to the question. You can have other designs, but you will need to figure out how you're going to use the address bus, data bus of the computer system to control a simpler ADC chip like ADC 670, this chip. For the next set of slides, we're going to look a little bit more about the PIC microcontroller. Before I go into a lot of details, how many of you have learned PIC microcontroller in the past? Okay. All right. About half. So it's a tough call. Okay. So let me just go through the set of slides. I'm going to run a little bit at faster pace because I want to have some time at the end to talk about the first lab. Now, do not expect that you will learn everything about PIC and become a PIC guru after today's lecture. For those of you who are not familiar with the PIC, you are expected to take a book, go online, find some examples to learn programming the PIC or from doing the lab. Okay, we talked about this. Let's go straight to the PIC microcontroller. It is an embedded microcontroller, has a small number of instructions, It supports interrupt, consumes low power. It has a lot of peripheral features, GPIO pins, ADC, timer, etc. It has a lot of special features, internal oscillator, power saving, sleep modes, etc. This is a block diagram. We took a quick look at it. I will skip this part to this is the pin layout. Okay, Harvard architecture and von Neumann architecture. This is two different architectures in terms of how the memory subsystem is connected to the CPU. Okay? The reason I'm bringing up this is we are going to use two different processors in this class, PIC and Intel Atom. And they follow into each of these two different categories. PIC microcontroller follows to the Harvard architecture, where you can see that this processor has separate data memory and program memory. And when this processor operates, it's going to load instructions from the program memory, decode it, execute it, and using the data from data memory. On the other hand, Intel Atom and any recent Intel processors follows the von Neumann architecture, where the program and data are stored in the same memory subsystem. So the processor will load data, programs, instructions from the same memory subsystem as the data. Okay, instruction pipelining. This is the way the microcontroller, PIC microcontroller, improve its performance. It tries to overlap the execution of consecutive instructions. Program memory space. I want to spend 1 minute on this. This is the program memory space. Imagine that you have a separate address space for data. By address space, we mean a region, a memory region that begins with 0, ending with some maximum value. That's the size of the space. This is the program memory space. You see it starts from 0, ending at, in this example, 1FFF. You have a separate box, separate address space for data. That's for the PIC microcontroller. We have two special addresses in this program address space. Address 0 and address 4. Address 0 is the the reset vector. Reset vector is where the first instruction is stored. When you power on the chip, when you reset the microcontroller, whatever instruction stored at address 0 will be executed. Typically, it's a jump instruction. Will jump to other parts of the program memory to start the main program. The second special address is 004. That's the interrupt vector. Interrupt vector, again, this is the address that stores the first instruction of the interrupt service routine. You can use interrupt for your ADC. You don't have to, but one option is to enable interrupt for the ADC. Interrupt will be triggered once ADC conversion is completed. You can then, by design, you can stuff a special segment of code to handle this case. For example, if you want to read the value from the special registers to another place, another register, you can have this interrupt service routine and have the first instruction of that special segment of program located at address 4. This slide shows you the data memory space. As you can see, we have address 0 at the beginning, and it goes on to some larger value. The data memory space has a lot of data, of course, but some of them are special data. And in PIC's terminology, these special locations are called special function registers. In some cases, well, you will see these data memory are also called registers. Each of these locations can be viewed or regarded as a register. And in fact, these are based on SRAM, on-chip SRAM. What you see here, these locations with names, those are all special function registers. From their names, you can roughly figure out what are their functions. There are also some locations, for example, from address 20 to address 5F, those are general purpose registers. Those are without specific names, and you can use these locations for storing your data temporarily. We'll shuffle things around. For the PIC microcontroller, you will have to use a lot of special function registers, okay? Including, for our purpose, the ADC. We're going to deal with special function registers. In the next few slides, I'm going to just introduce a few of them. We already talked about this special addresses. This is a part of the table of special function registers. What we see here is first column is the address of the register, and then the second column is the name, and the rest of the columns are the meanings of each of these bits in the register. All the registers are 8-bit. Let's take example here 03, address 03. Its name is status. It's a special function register, and its function is showing you the status of this chip. By status, we mean, for example, this carry bit, digital carry, 0-bit. Those bits are reflecting the result of the last computation, addition, subtraction, etc. Also, in this register, we have RP0, RP1, and IRP. Those are used in addressing modes, which we'll talk about next. Okay, this slide shows you a little bit more about this status register. By the way, this again is taken from the datasheet. So if you get the copy of the PDF file, you can find the information of every single special function registers. PCL and PCLATH, think about these two registers as the program counter of the chip. Program counter is the address pointer to the next instruction to be executed. Okay? You have this program counter in every processors, okay, to track the execution of the program. In PIC, this is implemented using two separate processors. I won't go into the detail, but just keep in mind that these two processors give you the information about which instruction is going to be executed next. And you can change the value of these two processors so that you can do a branch or jump. Okay, you can jump to a different place by putting a new value in these two registers. Stack is a small space, special memory, which is used to store the return instructions. Return instruction is associated with the procedure calls or function calls. You can have subroutines from your main function. You can call these subroutines, but in order to get back to your subroutine, to resume the execution, you need to store the return address. And this stack memory is used to store these return addresses. Okay. Again, this is a data memory map where you can see this data memory consists of special function registers and general purpose registers. special function registers, or SFR, are used to control the operation of the device. And general purpose registers, GPRs, are areas for data storage and scratchpad operations. GPRs are usually at higher address than SFRs in a bank, but higher means larger value. And different PIC microcontrollers may have different number of GPRs. An important concept in PIC microcontroller is called banking. This is talking about data memory. We partition the data memory in different banks, and each bank has 128 registers. Okay? And when you want to operate on either SFR or GPR within a bank, you have to first select that bank. Let's say if a PIC microcontroller has 256 bytes in the data memory, that is to say this data memory has two banks, bank 0 and bank 1. Okay? Each bank has different registers. And if you want to access a specific special function register, you have to switch to the bank. Okay? Well, I'm kind of speeding up here because we got a lot more information to cover. Bank 1 is used to control the actual operation of the PIC. What do we mean by that? For example, we can use the special register in bank 1 to tell the PIC that for one pin, one particular pin, physical pin on the chip, we want to use the pin as an input. Okay? Give you an example. When we do ADC, okay, we will need to get the voltage to the chip, so we have to have an input pin. So the way to say this pin A0 is an input pin is to use a special function register in bank 1. Okay, to indicate, to specify this way of using this pin. Okay, this is what we mean by control the actual operation of the PIC. On the other hand, bank 0, the registers in bank 0 are used to manipulate data. Use the same pin as an example. If we use pin 2 as a input pin, a digital input, we can use a register from bank 1 to configure the pin as an input. But if we want to get the actual value of that pin, we need to access the special function register in bank 0. Okay? That's what we mean by manipulate the data. We have a number of special function registers showing on this slide. W is the working register. It is used to move values from one register to another. FSR is the file select. INDF is the indirect addressing mode. And PC is the program counter. We've seen the status. Here, this slide, I want to spend maybe 2 minutes on this. Direct addressing and indirect addressing. Addressing or addressing mode refers to how the microcontroller finds its operand. Assume you all understand the meaning of operand. Talking about assembly language, you have the opcode, operand. If you do A plus B, A and B are operands, and plus that operation is the operation. So when you have such an instruction, you want to tell the microcontroller or microprocessor where are these operands. If you want to do A plus B, where is A, where is B? Okay? That's what we mean by addressing mode. In PIC microcontroller, there are two ways to specify using either direct addressing or indirect addressing. Okay? In direct addressing mode, the way to specify the location is to use this bank select value coming from the status register and the location. To put it simpler, in direct addressing mode, we select the bank, okay, by taking these two values, so we know which bank. And by looking at the location value from the instruction itself, we know which location in the bank. Okay? So, 2 steps. First, find out which one of these banks. In our case, 4 banks. If we have 0, 0 here, we know that's bank 0. If we have 74 here, that means 74. So we can locate that value. And then we're done. The microprocessor is able to grab the value to perform whatever operation. Okay? For indirect addressing mode, the goal is still the same. We must get the bank ID and the location in the bank. But the way to get these two values is different from the direct addressing mode. We will use so-called FSR register, file select register. This is a very special register. And we're going to use the values from this register plus this IRP bit from the status register to find out exactly which bank and which location. Okay? And the next slide shows you an example how we switch banks and how we access locations within the bank. Due to the time limit, I have to skip this and the next one. Well, these addressing modes are important for you to understand the internal operation of the PIC microcontroller. In your first lab, most likely you're going to use C as the programming language rather than writing assembly language directly on the chip. So in that case, when you use a high-level language, you don't really know or care about the underlying addressing mode. The compiler handles all the translation from the C program to the assembly language program. But still, it's important for you to understand because later you may need to analyze the assembly language program, or you need to do debugging at the assembly language level to figure out exactly what's going on underneath. Okay, this slide is talking about how we do the I/O. I touch upon a little bit. We talk about using bank 0 to tell PIC how to use the pins, and use a register from bank 0 to get the data in or out. Coming back to the I/O, we do the same thing. For any I/O port, A, B, C, D, or E, we have basically 2 registers we use to either control the operation or manipulate the data. Try S, A, B, C, or D, port A, B, C, or D. This try SA, for example, is used to specify the operation of port A. Try SA is 1 register. Okay, picture that you have 1 register. Try SA. This is its name. It has 8 bits, and each of these 8 bits corresponding to a pin of the chip. Okay, so bit 0 in try SA corresponds to A0 of your chip. Now, on this try SA 0 bit, you can have 2 values, 0 or 1, right? If you put a 1, you're going to use this pin as an input. If you put a 0, you're going to use this pin as an output. It's very simple, right? You can picture it. 1 is input, 0 is output. So that's how we're going to use try SA register to do that. Its counterpart is port A register. That's the register you need to use to get a value from the input pin or send a value out if it is an output pin. Okay, so we're going to use try SA and port A often time together to operate on these I/O pins. Okay, so let me move on to the PIC-based sensor data acquisition. Yes. Tri-state, that's right, yep.
If you say it's 2,
You can also put it as a high impedance, but its name comes from the fact that it's designed as a tri-state buffer type of structure for those I/O pins. If you look at the internal design, you understand better. Yeah. 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 If I hear you clearly, can you say that again? Yes, so you can use it as a analog input. For example, for our purpose, we want to have a input for our ADC. You can also configure it as a digital input and output. Okay, let me move on to the PIC-based sensor data acquisition. This is the major part in your first lab, so I would like you to pay close attention. This is the block diagram of ADC in this PIC 16F684. Although we're going to use a different chip, but the architecture, the principle, the way to program it is almost the same. This particular ADC has a 10-bit resolution. You can use either the reference voltage coming from the outside or from using the supply voltage of the chip. That's what we call the reference voltage software selectable. This ADC can also generate an interrupt upon the completion of a conversion. Okay, just looking at this diagram a little bit, we have this ADC here. This is the ADC unit that does the actual conversion. We have a number of inputs that we can select, depending on which pin you want to use as the input pin for getting the sensor voltage. And the way you select is to use this CHS. We have 4 bits here. Okay. CHS, you know from later slides that this is a part of the configuration register. Okay. The way to select these different options, different pins, is by setting the values of a special register. Okay, that's the idea. And this idea applies to many other options you're going to choose while doing this ADC conversion. For example, here you can use VCFG. This is 1 bit from a control register, ADC control register. If you put 0 on this bit, it's going to select the VDD, the supply voltage, as the reference voltage. So your input voltage you're going to compare with this VDD. If you put 1 on this bit, it's going to use external reference as the comparison reference. Okay, so you can do that by setting the value, proper value of this bit. This go and done, you can guess that this is the control, right? You say go, that means you want to start a conversion, and once the conversion is done, this will be a 0. And AD on is another control signal, and ADFM is used to decide how you're gonna fit the final value in the registers. This ADRSH, ADRESL. This is the ADC result, high and low. Okay, because this is a 10-bit value, you're gonna need 2 registers to store it, and you have the option doing left adjustment or right adjustment. Okay, that will determine how you interpret the final result. coming from these two registers. Here's a list of the registers that you need to look at, and their bits you need to carefully configure in order to perform this ADC. Port configuration, you will need to determine which pin to use as the input. You also need to set proper mode, analog or digital, and you need to decide which channel, okay, which one of these 8 pins. You need to select voltage reference, and you need to decide which clock you want to use. And if you choose to use interrupt-based method, you will need to do this interrupt control. And finally, you want to decide how you're going to format the data. This is a table from the data sheet that lists the registers related to ADC. And from the PDF, you can actually click these names, and you can get to the proper page that gives you more details about the exact register. So just we talked about ADC control 0, where you can see this is the format selection. This is the configuration bit to select either VDD as a reference or external reference. And the values listed here are the default values upon reset. This is the table that explains Tri-S8 register. We have, for this particular chip, we only have 6 of them from 0 to 5. I mean the number of pins on A port A. So we have Tri-S8 5 through Tri-S8 0. And if you put 1 on these values, then that's going to be configured as an input. And if it's 0, it's configured as output. Next register is the analog select register. You want to configure an I/O pin to be input mode for analog signals. Then this is the register you need to set proper value. Okay. As explained here, when it's 1, it is an analog input. When it's 0, that's a digital I/O. Now we're looking at this ADC control 0, AD controller register 0. It has all different kinds of control pins, including this channel selection, these 3 bits. And it has a go/done control signal and AD on control signal. So let's look through this. The first one, ADFM. This is the AD conversion result format selection. And the next one is the voltage reference selection. And next 3 are used to select the input channel for the ADC. And this go/done, this is the AD conversion status bit. This is the bit that you will need to look at if you want to keep checking or polling to see if ADC is completed or not. If this bit is 1, that means it's in process. If you set this bit, means if you write 1 to this bit, it'll start another ADC cycle. When you read, if you read a 0, that means the ADC is completed. The very last bit, bit 0, is the ADC enable bit. And of course, you want this to be enabled. Clock source, will give you options on different clock settings. You can choose based on the need. Okay, this slide shows you high-level picture what we should go about on ADC operation. For starting the ADC conversion, we will need to write 1 to the AD on bit of the AD control 0 register. It's basically turn on the ADC module. To actually start the ADC conversion, we need to write 1 on the go/done bit of this control register. Okay? So we need to have these two separate instructions. Now, once ADC is in progress, you have to wait a little bit if you do polling. The way to check whether the ADC is completed is by reading the go/done bit of AD control 0 register. The other option is to use interrupt. You can enable the interrupt and write an interrupt service routine, so you don't have to do polling, because polling actually takes CPU cycles. You have to keep checking that bit. As a result, you cannot do anything else. And you can terminate the ADC by writing a 0 to the go/done bit. All right, to summarize, to perform this ADC conversion procedure, you need to follow following steps. Very first one, you need to configure the port properly. You need to set the pin as an input pin, and you want to set it as analog. And after that, you will need to configure the ADC module. By that, we mean you need to set proper values of ADC control register, or maybe registers, depending on what function you use from the ADC. This includes to select ADC conversion clock, to configure the voltage reference, either the VDD or external reference. You need to select the proper ADC channel. You need to select the result format, left adjust or right adjust, and you need to turn on the ADC module. If you want to use interrupt-based ADC, you need to perform additional operations in terms of clearing the ADC interrupt flag, enable the interrupt, enable peripheral interrupt, enable global interrupt. This peripheral interrupt and global interrupt are mask registers that could be used to turn on and off certain interrupt signals. So you need to properly set all these control registers. And after that, you will need to wait for the required acquisition time in order for the conversion to complete. You will start the conversion by setting the bit. Wait for the conversion to complete by one of the following. If you do polling, that means you have to keep checking the go status done bit out of the control 0 register. If you do interrupt, you don't have to wait. You can do something else. Once the interrupt happens, that's indication of the completion of conversion. So either way, you will be able to read the final ADC value out of those two registers, AD result high and low. And for the interrupt, you need to clear the interrupt flag.